Today, what I'd like to start talking about are functions and passing parameters back and forth between functions. Um, how you can do things with multiple C files. Okay, so not everything has to be in one giant C file, just like in Python. You can have, put this function over here and have your main routine there and call it between the two. Um, well, also, I want to talk about some of the other data types. Um, we haven't specifically looked at strings or arrays yet, although we've talked about that they exist. Um, and so want to look at that a little bit more, and then start to kind of get into how this stuff is actually stored in memory and one of the debugger tools that will let us kind of see how things are stored in memory. Okay, so oops. So the main function here actually gives us a good example of uh, the definition of a function. Okay, so there are three components to when you define a function. There's the name of the function, which for uh, in C anyway, the main function has to be called main, and then you can have other functions that are called other things of your choosing, but the main one's got to be main. Um, and then there's a data type before it and stuff in the parentheses. Okay, and not every function is going to have the exact same parts either before or after, but it has to have all three of these components. Okay, now the name of the function is, like I said, just what it's going to be called when you utilize it. So that's kind of up to you, with the exception of the main function. Um, the stuff on the outside is the data type of the returned thing, if any. Okay, so it's an int here because I'm going to return the integer 0 to the operating system. Uh, and the convention in Linux, anyway, is that returning 0 is basically just signaling that the program terminated correctly and cleanly and everything went fine. Okay, um, so that's why I've just made this return 0. Okay. And then the void that's inside the parentheses, what goes in the parentheses is any variable or variables, plural, that your function takes in as an argument. Okay. Now, in our case, the reason I put void here is because the main routine is not taking any input, right? I'm not passing it any parameters or anything like that. And so just to tell the compiler, hey, there's nothing coming in, we specify void. Okay. But if I wanted to have a function that did accept a parameter, I would define what data type that parameter was and what its local name within the function is going to be called. Okay. Now, when I say local, let's go back to Python. Did you guys talk about scope at all? Right. So what's the idea of scope for a variable? Yeah, Jaden.
Certain variables can only be interacted in certain environments depending on what scope it is. So
Mm-hmm.
if you give it a global scope, it can be interacted anywhere in the code. But if you define the variable inside of a function, it can only be interacted inside of that
With
function.
it inside that function, exactly. Okay, so the scope would be if I define there are some things that I would want to define as global variables. So, for example, the constant pi would be a good one to define because it's a constant, it's not changing, and presumably, if you were writing like a program to do a bunch of math, like everywhere may need to be able to access that variable. Okay. Good examples of variables that are local are things, the counting variables that you use for loops, for example. Okay. So, in fact, let me go back over to our loop example from last time. So, here, our counting variable was the letter I, the variable I. What would have happened if I had put another uh, loop down there. Could I use I again? Yes. Okay. Now that's handy in the case of loops because, there's only so many letters in the alphabet, and so we typically just use I, J, K, M, N, those sorts of letters for our looping variables. And, if you're going more than like 6 loops deep, then you're going to have a really bad day because it's going to take forever to run. But if I tried to do something like here, if I tried to print I right there, this is not going to work. And why won't it work? Yeah, because it's not within the scope of I is not defined in the current scope. It only exists inside this for loop, and when you come out of the for loop, it no longer exists. Okay, and you'll notice that you see how there's that red squiggle underneath the I. In this case, it's because VS Code is doing a little bit of error checking for me before I even get to the compiling stage. So the fact that it's got that little red squiggle underneath is it's saying, hey, there's something wrong here. And in this case, the issue is that it's not within scope. Okay, so right, so that's the idea of scope. Okay, and we have to worry about that with functions. Okay, so let me write sort of the stupidest function ever. Okay, and I'm going to have this function square the number. Okay, now normally I would just do that like this, right? Just have it multiply by itself. Okay, but what I'm going to do is I'm going to make a function that squares this number, not because I need to make such a function, but just to illustrate how I would do it. Okay, so what kind of data type is my squaring function going to take in? And in this case, an integer. It could theoretically also be a float, but because I'm defining the number that I'm going to give it as an integer, I'll just stick with integer for right now. Okay, so that's not a big deal. And what kind of number is going to come out? Also an integer, it's just that thing squared. So the definition of my function will be something like this, okay? So what kind of input will it take? It will take an integer, and within the function, I'm going to call that num. I could call it whatever I want, but I'll just call it num. And what kind of data are we going to return from the function? Also an integer in this case. Okay, and so what should I return? Well, what's the computation I need to do? Num times num, okay? And I could just do that, okay? I could also do it in 2 lines and say num equals num times num, return num, something like that. Either of those would work. Um, Maybe the advantage of the second one, the one that's currently typed there, is it's separate. You're not putting too many things into one line of code, but it does mean that it's a separate second line of code. So whatever. Uh, okay, so is that good? Just, I mean, I know this is a stupid function, but it illustrates the idea. Okay, so I defined the thing down there, and then down here, let's do, instead of number times number, I could do square of number, right? And then let's print okay, the square is that value. Okay, good. All right, so let's compile it, make sure it works. functions. There we go. Square is 25. Yay. Now, in this case, by making my variable here number and then squaring it, is the original value 5 in memory anywhere anymore? So the value 5 is in memory here, but is it in memory after this line is completed executed? No, I overwrite it with 25. So it might be better, for example, to do something like this. Okay. And then what I can do is preserve the input value for posterity. Okay. I don't really need to here, but right. That way, if for some reason I still needed that number 5 for some other computation, I haven't destroyed that information. Okay. All right. So does this kind of make sense in terms of how to define a function? Okay. Now, what about if I had a function that had multiple inputs? Okay, so here I've written one that squared a number. Let's write a function that multiplies two numbers. Okay, so again, let's just stick with ints. Okay, and let's say that I take in two values, and I can take in essentially as many as I want, and they don't all have to be the same data type. Okay, so I could take in an int and a float and a string or something. But for this example, we'll just take in two integers. And so if I wanted to multiply these, what should I return? Just the product of the two. Okay, so nothing particularly special there. And then let's just put something in here. Let's do int a equals 3 and int b equals 7, and let's do int ans2 equals multiply of a and b, and then let's print, oops, okay, good. So let's run that, and there we go. Okay, so yes. Yes, I could, for example, so let me comment these out and do something like that. Is that what you meant? Oh, yes. Okay. So where I could ask the user to type, hey, what do you want A to be? Yes, totally there is, and we'll get to that. Okay. Um, we got to talk about a couple of other things first, though, before we get to there. So yeah, like in Python, there's the input function where you can just say a equals input of something, and then prompt the user, hey, please type a number. Yeah, totally, 100% we'll do that. Okay, and if you were writing like a calculator program or something, you would totally want that ability for the user to be able to input something. Okay, um, uh, and then let me change this back to what I had. The reason I haven't showed you guys that just yet is because the input routine for in C is a little bit more complicated. There's more things that we have to worry about than when you do this in Python, and we need to worry about those things first. Okay. Okay. So one thing that's sort of irritating, at least about the way that the functions work, is how many things can you pass to a function? Basically as many as you want, okay, with some details that we'll deal with later as to if you pass like 30 things to a function, how you do that versus if you just pass three. Okay. There's a convention on those sorts of things. But what is somewhat irritating is how many things can come back from a function. One single object. Okay. Now, if I had a function that I needed to write that needed to return three pieces of data, okay, uh, then I would have to put those into some sort of compound object like an array or a thing that we called a struct, um, or something, so that I'm technically only returning one thing. Now, it may have sub things within it, but I'd have to kind of structure myself in that kind of way. Now, for the silly functions we wrote here, this isn't really an issue because they're only returning a single number. But returning more than one thing is not as easy as it might seem. Okay, which is kind of irritating, but c'est la vie. I mean, you guys have to remember that um, C is essentially about a 50-year-old programming language in that ballpark. It's 1970s. Um, and uh, what fundamentally, I mean, this isn't 100% true, but uh, a good amount of why it was developed based on some predecessor languages um, was essentially to write operating systems. Okay, so who created C? Do you guys know? Well, who's the name on the book? Kernighan and Ritchie. Okay, has anybody ever heard of these two guys? No? How many of you guys took 242 last semester or are in it now? Did you guys talk? Did these two names come up? Okay. Huh? Well, and you haven't. Okay, so you may or may not have gotten them there. All right. So what else did Kernighan and Ritchie? Where did they work? Hmm? No, Microsoft didn't exist yet. All right. Well, who was doing all the like in the 1970s? Who was doing all the really awesome work on computers? What companies and what universities? Huh? IBM. Okay. Who else? Okay. Yeah, that's a little earlier, like 50s and stuff with Eckert and Moakley. Yeah. Yeah, MIT, some of the schools in California, Berkeley, Stanford, places like that. But a big one was Bell Labs, right? And which is to say, they became AT&T, right? Why the heck would they be interested in computing and stuff? I mean, where do you think the transistor was invented? It was invented at Bell Labs, not a school. Um, yeah, why would a phone company care about computing stuff? Well, okay, it's 1950. You want to call somebody in your family. How do you actually make that phone call in 1950? Yeah. Right. So you'd pick up the phone and the operator would be at the other end and and it was usually women that did this. Operator. And you'd say, "Yes, I'd like so and so." And they'd be like, "One moment, please." And then there would be like literally a giant board in front of them with a lot of plug holes, and they'd have a bunch of wires, and they'd connect your plug to whoever you were calling's plug, and then there were lights so they knew when the call was disconnected to then unplug it so that and as you could imagine, this was a giant mess. What about if you wanted to call long distance? Yeah, or you'd have to know certain codes. So, for example, has anybody ever heard it's sort of a big band swing song called Pennsylvania 65000? No? Okay. Well, that's how you used to have to do sort of long distance. You'd give them an exchange number and they'd connect you, but you may have to talk to multiple operators along the line, right? And turns out that if you wanted to dial long distance in the 50s back here to get to Crawfordsville, the exchange code was Emerson 32000. Um, it, don't ask how I know that. It's not because I was around in the 50s, right? Okay, but like, let's say when you guys were kids, before you had cell phones, how did you, if you wanted to call somebody, how would you do it? You'd pick up the phone, there'd be an array of buttons, you'd hit the correct sequence of buttons, and then it would start ringing, right? So, who connected your call then when you were pushing that sequence of buttons after you finished the sequence? It was a machine, right? Not a lady sitting there that says, one moment, please, right? And connects you, right? And so as telephony got more and more common in the world, and now everybody has a telephone, uh, the having the people in the switchboards manually plugging things together, is that really practical anymore? Like, can you imagine if that's how phones worked today? No? Well, exactly. Like, you'd have to wait 30 minutes just to get connected to the pizza place, much less order a pizza, right? That would kind of suck, especially if you're hungry and you want that pizza, damn it. Um, okay. So anyway, they worked at Bell Labs, and one of the things that they had were these big computers, PDP-7, later PDP-11, and these machines were so fast that so like in the 1950s, if you had a computer, how would you load a program into it to run? Floppies in the 50s? No, they had punch cards back then, right? You'd load in your deck of punch cards, it'd run through the machine, it would spit something out, and you'd go and collect that. And usually they ran these things overnight, right? So an operator would take the stack of cards, put it into a reader, and so on. So the one of the reasons that a language like C was sort of designed is, so one of the other things that these guys did when they were at Bell Labs was they designed several operating systems. Multics was their first one, and it was meant basically as a giant program that would manage the computer and manage all the different people using it running their little programs and keep everything orchestrated so that nobody was doing things that they weren't supposed to be able to do. Nobody was destroying each other's data. Um, let's say, for example, you had in a university, if there's no restriction on who can read and write what data, then if you're a student and you've got access to this computer, and I'm the professor and I also have access to this computer, and let's say I'm writing an exam for you guys, then what could you do? Yeah, you could get on there and find it, right? Well, that's not a good thing. Maybe it is for you guys. I don't know, right? And so the idea of an operating system would be I have some files and you have some files, and you can't see my files unless I give you permission to do that. So they wrote operating systems, and the first ones, they had to write them basically in assembly for whatever machines. But let's say you do it in assembly for a PDP-7. Well, what are you going to do if you then try and run that on an IBM model computer instead of a DEC computer with like the PDP-7? Well, it's a different machine, different architecture. Okay, so you need something that's low level enough to do things like memory and get nitty gritty, but still high level enough that it's sort of machine independent, and thus became C. So they designed this language, and then Multics was their first operating system at Bell, and it was kind of over-engineered, to be honest. And so they decided to make something that was a little bit more um, lightweight, and that was Unix. Unix version 4, they rewrote most of it in C so that it would be platform as independent as possible. But in particular, what's Unix? I mean, operating system, but what do we get from Unix? No? Linux? The Macintosh operating system derives from Unix. That's two pretty big operating systems, right? So both of the computers sitting on my desk are running a Unix sort of uh, grandchild, if you will. Okay. Um, right. Okay. Anyway, that was a long digression. Why did I get into this talking about Bell Labs in the first place? Well, yeah, ultimately that's why, yeah. But okay, so there's some of the history. I'm sure I'm, forgetting a lot of the details there, but um anyway, okay. So right. So that's our stuff for functions. Do we have what questions do we have about the functions stuff? Okay. For now, it's okay. Okay, so I'll give you guys something to do that involves functions um, for a new assignment. Okay, so let's also talk about, let's go back to data, or actually, let me make a new folder, and we'll call this strings and arrays. Okay, and let me close these guys, and let's get a new file. Oops. I have to say, guys, I really have been finding VS Code to be a really nice IDE. I never used it until very recently, but it's really actually quite nice. All right. Well, yeah, that's part of it. But the other thing that's made me really kind of switch to it is the other program that I really liked to use for doing, IDE stuff like this, called Atom, uh, is going to get discontinued, and that kind of sucks. Partly because I think a lot of people are switching to VS Code, and so they just decide it's not worth the trouble. The other thing is, and I have to give it to Microsoft, um, that for making VS Code, like I can run it on Linux, I can run it on ARM Linux, I can run it on x86 Linux, I can run it on my Mac, I can run it on Windows. Yeah, they don't care. It's like you got a platform, VS Code will run on it, and um, that's kind of nice, to be honest, because you can use the same IDE with all of the same extensions on any platform. And there are a lot of nice extensions also that, there's a good developer community around it. Okay, so um, so let's talk strings and arrays. All right, so let me define. Um, so we've defined strings when we used printf, okay, and we haven't defined an array. But what's basically the idea of an array? Hmm? Yeah, a list of objects, okay. And for an array, it's usually numerical objects that you do this with. So you have like an array of numbers. And if I have an array of characters, guess what we call that? A string, right? Okay, so how do I define a string or an array? Sorry, make sure that I do the right thing here. What was it I wanted to look for? Right, and I did mention, by the way, that the Bible here, right, is online, free, and everything. So make sure that you take a look at it because it's really, really quite handy. Okay, so um, an array, I need to specify, well, what kind of pieces of data make up the array? Okay, And let's just, for the moment, take something numerical. So last time we wrote that loop function that basically just printed this, printed a bunch of numbers, okay? And what was one of the assignment I gave you guys that was sort of to update that a little bit? To print the numbers and their squares next to them. Okay, so we could have done that sort of thing with an array construction and keep the numbers in one array and their squares in the other, rather than computing them as we go. Okay, either way would have worked fine. All right, so let's just, oops. Okay, so this is how I'm going to define an array, is what kind of objects go into the array, the way I've typed this. They're integers. They could be floats, they could be doubles, they could be whatever, right? I'll just take ints for example here. And then I can define, you know, however many I want there as so, okay? All right. Now, the thing in the bracket, right now there's no thing in the bracket, okay? Um, but I can put a number there in the bracket to indicate how many things are going to be in this array. If I know that number in advance, or I want to create an array with a specific amount of things in it, then I can do so. Or I can initialize it, in this case, how many things are in that array? 6 things, right? Um, and that's simply because I picked the numbers 0 through 5. Okay. So you can do it either way, just sort of depending on do you know the contents of the array from the get go, or is it something that you're going to kind of construct as you go? Okay. How does this compare to Python, by the way? What do you guys, to a Python array? Yeah.
Well, depending on if I go back on if you just like put that array like inside that first paragraph in Python.
And now I'm actually blanking on how you did this in Python, but yeah.
You just give it a name and then set it equal to and something in brackets and you just write the rest. Oh wait, yeah, that's what I'm thinking of. Where like you just have a variable, you can just set it equal to.
Yeah, you do something like my array equals,
Yeah.
right, or whatever, right? And yeah, so okay. Now, like in Python, though, let's say that I wanted to pluck out a specific element of the array. So let me actually change my numbers here from that just to something a little less contrived. Okay, so I just picked some digits from pi. Okay, no big deal. Let's say I want to access the number 3 that's in this array to do something with it. Okay, how do I get that number out of the array?
Like an index, right?
Yeah, it's indexed. Okay, and so I would basically do something like, let's say I wanted to print that particular one. So let's just say %i backslash n, and then which thing from my array do I want to pluck out? I want to pluck out the first element, okay? But how are things indexed in C? Basically, always they start with 0, not with 1. Okay, that you guys should be relatively used to, right? That, I mean, by this point, okay, great. So I'm going to start with the object number 0, which is the first one, and then so on. Okay. All right. So let's just run this real quick and make sure we're good. Um, and let's see, what directory did I put this in? Let's see, strings and arrays, and okay, and it printed 3. Okay, nothing particularly exciting there. But the fact that you can index here by whatever means that you could iterate through a string, for example. So let's say that, so the assignment I gave you, number one, which was just to take the number 0 through 9, right? And there was nothing special about the number 9. Print the number and its square. So you'd end up with, 0, 0, 1, 1, 2, 4, 3, 9, and so on down to 81. Okay. We could have redid that with an array where you would put the numbers, say, 0 through 9 into an array, and then you'd have a second array to hold the squares. Okay. Yeah. Okay. But great. Nothing particularly exciting there. Arrays can be, so what can you make an array out of? Like here we did it with integers, but what else could we have done? We could have done floats. We could have done long ints, which would be 64 bits. We could have done doubles, which would have been 64-bit floats. Okay. We could have done what can, sorry. Yeah, we could have done strings. Okay. So what is a string made out of? What's the fundamental data type for a string? A character. Okay. All right. So a character, let me just start with that. Okay. Could be something like this. Okay. Now, the letter A here, or capital A that I've picked, just for sake of example, that's a specific character. But I think I mentioned either last time or maybe it was the time before, that character is also the how we do 8-bit number, like 8-bit integer arithmetic. It's also how we do letters. Why are they the same? Okay, well, how is the letter A actually encoded? Yeah, it's in ASCII. Okay, now, how many of you guys have not talked about ASCII before? Okay, in Python, how is stuff encoded? Well, everything's in binary ultimately, but what I mean when I say encoded is, right, ASCII is a scheme of taking letters and stuff and putting them into a particular binary pattern. And if we all agree on that pattern and you hand me a binary pattern, then I can be like, oh, it's the letter A, or whatever. And in fact, actually, how many of you guys have seen The Martian, the movie, right? Well, I know you have, right, because you were in that tutorial with me. Um, what what was one of the cruxes of the communication difficulty that once they realized that he was alive and he drove out and he found that old rover that had a camera on it? Like, how did he communicate actually with everybody? Huh? It was initially yes or no, and then he dug around in the space base or wherever he was, right, and rifed through all the other astronauts' things, hoping that one of them was nerdy enough to have packed what? The ASCII table, right? So then he put 0 through F around his little camera thing, and they sent him, and he encoded messages in ASCII, and that worked great, right? Okay, so it's encoded in ASCII, and so the letter capital A here is really like 40 something in hex. Okay, now where do we find that? Well, we actually had our ASCII table from last time. So where is capital A on here? Yeah, decimal 65, hexadecimal 41. Okay, so the when I've typed A here, that's really the decimal number, or sorry, integer 65. Okay, but if I print it, it's going to print it as the character or the number. Okay, and we'll actually look at that in just a second. Okay. Okay, so, right. Okay, so I've defined here a character, and I just picked A for no good reason. Okay, But one thing is, how do I designate a character? It's sort of like, how do you designate a string in Python? Like if I wanted to make a string with my name in Python, what would I have to put around the contents? Yeah, the quotations, right? And one of the things that was both nice and irritating about Python is that there were lots of different ways you could do that. You could put a pair of double quotes. You could put two pairs of double quotes. You could put three pairs of double quotes. I mean, it's kind of like Oprah, right? Like you get double quotes and you get double quotes. You could have as many as you freaking wanted. I mean, not really, but um, characters, you use a single quote. Okay. Strings, you use a double quote. Okay. So I've defined there my character. Okay. And then if I wanted to define a string, it's essentially just an array of characters. Okay. Um, something like this. Okay. Now let's make this thing print my string and also my character while we're at it. Okay. So I'll still print the number. I'll just leave that as is. And I could do printf, for example. All right, so if I want to print an integer, I have to have a format code, a percent something for the integer. Okay, if I want to print a character or a string, I have to also have a format code for that. Okay, and what should the format code for character probably be? C makes sense, right? Okay. Um, and then I'll pass that, what did I call it? My car. Oops. And then, oh, let me put a line break there. Oops, print F. Okay, and then what about the string? What do you think that one is? That seems logical. Oh, and I'll do a line break. And then I called it my string. Oops. Ah, there we go. Okay, so let's compile and run this. And there we go. Okay, so the um, and if I wanted to access a particular letter out of my string, could I do that? So if I wanted to access, for example, the capital H, what would I have done? My string of 0 is a character because it's only a single character then, not a full-blown string. Okay, so great. So that's not, particularly exciting. Now, you guys maybe wondered, for example, oops, I wanted back up here. Those top two lines of my program, where I'm including stdio and string.h. Okay, the reason I needed to do that is because I'm using, well, up until, well, actually now, we're still not actually utilizing anything from string.h. Okay, we are using stuff from stdio when we're printing. Okay, and so if I remove that, then printf basically wouldn't work correctly because I'm not including the library that has that. String.h has a bunch of things that you might want to use for string processing. Okay, so what kinds of processing on a string might you want to do that would be potentially useful? Well, what did you guys do when you did this in Python? Like, what about strings might you want to do? You want to maybe put them together, so concatenation. What else? Okay. Sort of the opposite of concatenating, being able to break them up into individual pieces, separate substrings. Okay. You might want to be able to calculate the length of a string. How would you do that, by the way? Huh? Well, you could do that, right? Like if you had a function, there is one, it's called strlen, string length, right? Then, yeah, it can tell you what the length of the string is. But how fundamentally does it work? Like if you didn't have that function, how would you do it? You'd have to loop through a string until you hit the end of it. Well, that begs a very, very important question, which we'll come back to, which is how do you know you're actually at the end of the string, right? Okay. Okay, so we'll talk about that in a moment. Um, okay, but yes, I could get out the letters that I wanted, and I could get out, you know, there are functions to do string processing. We'll talk about some of those later, because to really get the oomph for example, with the string length function, okay, is one assignment that I'll give you guys will be to write your own string length function and then use the built-in string length function to make sure that you're getting the correct answers, right? Okay. The other thing I want to talk about, so we've got sort of a couple of questions that we need to hammer here. One is, how do I know that I'm actually at the end of a string, right? And the other thing is a little technical, and this will kind of get us into our discussion of what are called pointers, something you did not have to deal with in Python. So printf is a function, right? Yeah. And I'm passing printf some data. I'm passing it strings. Am I really passing it a string? Okay, that's maybe a technical or philosophical question because it's sort of, and maybe it's poorly worded. I'm not really passing it a string, okay? And for architectural reasons, I can't pass a string the same way that I would pass an integer, okay? And the reason for this is how a processor is actually constructed. So, inside a processor, okay, if I want to add two numbers together, where do those two numbers have to be? Okay, so those of you guys who did 101 with me. Registers. Okay, so inside a processor, okay, there's a hierarchy of memory, okay, and the biggest pool of memory that you have at your disposal will be your hard drives, okay, and those are useful because they store data when the machine is not on, okay, and they can hold crap tons. Okay, one level up from that is your RAM. How much hard drive space do you have on your computers? Yeah, possibly on the order of multiple terabytes. How much RAM do you have in your computer? Yeah, 16 gigabytes, 32 gigabytes, maybe 8 gigabytes, depends on when you bought your machine, how much you splurged, right? Okay, speaking of which, is anybody looking for a pair of 16 gigabyte DDR5 sticks? Because I got two for sale, and they're on the classifieds. I was tempted to send an all campus email, but I knew how that would go down. So, um, yeah, anyway, I've got some DDR5 sticks for sale in case anybody's interested. All right, so anyway, but how much RAM do you have? You know, like no more than say 32, 64 gigabytes, somewhere in that order, okay? Which is essentially an order of magnitude smaller than your hard drive space. Okay. Now, get into the processor. How much memory is internal to the processor? And what is that memory called? You guys know who's built or bought a computer in the last, say, couple months? All right. Well, let's just go shopping then, shall we? Nope, that's the speed at which it operates. That's frequency. All right. Well, so did anybody watch the AMD Risen 7000 series uh, thing on Monday? All right. So AMD announced their newest batch of processors Monday night. And let's just go to, I don't know, I don't really care which website, okay, where they've got some of the details as to, okay, what's the, how much is it going to cost and How much things? Okay, so here we go. So the flagship processor, 16 cores, 32 threads, boosting at 5.7 gigahertz, which is pretty fast. 170 watts. That's pretty hot. $700. Okay, but this number right here. Okay, 80 megabytes. So yet another order of magnitude smaller than the RAM. Okay, so cache, it is RAM essentially, right? But it's on board the processor. It is way faster than RAM in the same way that RAM is way faster than a hard drive. Okay, but there's only like 80 megabytes or so of it. So what gets loaded into RAM? Or I mean into cache basically. When you're running a program, the stuff that you're currently executing is actually in cache, not out in RAM. Okay. Um, and then, but if I want to add two numbers together, okay, they're in very special dedicated little memory cells called registers. And how many of them for doing integer computations are there in the processor that's inside our Raspberry Pi? Anybody know? There are 32 of them. They can each hold 64 bits. Okay, so that's not a whole lot in some sense, but it's ludicrously fast. Okay, so like in comparison to, say, your hard drive. And when I say ludicrous, I mean like in the sense of Spaceballs, right? Like where, you know, oh, he's gone plaid. No, none of you guys have seen Spaceballs. Okay, I'm very disappointed. Very disappointed. Okay. Um, okay, good. So, um, so let's think about this. If you have 32 of these general registers that each can hold 64 bits, how big is our string in terms of how much data it would need to for us to store it? Okay, so how many things are in my string? 6 characters. Okay, um, counting the exclamation mark. That means that the string would require 7 bytes to encode. Why the seventh byte? Because you think, oh, wait a minute, but there's only 6. Well, I have to put something at the end to say, hey, this is the end. Okay, and that's where that extra byte comes from. And each character is stored in precisely 1 byte, 8 bits, okay, because that's how ASCII works. Okay, so I can't really pass a string in the same way that I can pass an integer because, well, okay, yeah, this string is really small, but what about if I had a string that had like several thousand characters in it, right? Then it would be take up too much memory. It wouldn't fit into a register the same way that a number does. Okay, so the answer is that I'm not really passing a string to the function. I'm passing something related to the string, namely where it is in memory. Okay, so I'm passing a special number to it. Okay, so it would be like this. Um, let's suppose, well, okay, actually, here's a good example. So my parents, they retired last year and moved to the same town where my sister and her husband live. It's clear which child they like better. Okay, um, or rather, which child's geographic locations weather they like better because they don't like snow, and so hence they're not coming here. They're the move here. Okay, anyway, so their particular neighborhood, they don't have mailboxes out front of their house. Okay, like many neighborhoods do. So where do they go to get their mail? Not straight to the post office. I mean, you could do that. Okay, but around the neighborhood there are these big like mailbox like zones, almost like an apartment complex. Okay, where or the mailbox is down in the basement of the of Sparks. Okay, so let's say that my dad gets something from Amazon that's too big to fit in his mailbox. Then he opens up his mailbox, what does he find in there in addition to some mail? He finds a key. The key has a number on it. And down below all the regular mailboxes are giant mailboxes for packages. And so he looks at the key and he says, oh, my package is in box number 5. And so he puts the key in box number 5 and unlocks it, and there's his package. Okay, so the package was too big to fit in his mailbox. Yes. So what did the post office give him? They didn't give him the package, but they gave him a thing that told him where the package was. And that was enough for him to then go and get the package. Does that kind of make sense? So pointers are basically that idea, right? If I have an object that I can't necessarily just pass around because it's too big to fit in certain places, what I can instead do is pass somebody the location of it rather than the object itself. And the location of it is called, or like the data type that holds these locations, those are called pointers. Okay, is that okay? All right, so how do I find out where the heck this string is in memory? Okay, so what I'm going to do is let me print another thing. Okay, so, oh, and let me throw a line break in there. Okay, so if I have an object, I want to know where that object is in memory, I can access that by just getting putting an ampersand in front of it. And that says, okay, I don't want to know what the thing is, I want to know where it is. Okay, now, what data type holds these locations? Or like what kind of data do I need to encode the locations? So in my dad's mailbox case, it was just a number from 1 to 12 or something, okay, corresponding to the big mailboxes. For us, it's going to correspond to a memory address. Okay, well, this begs the question: how much memory is in our Raspberries or in your computers? Okay, so RAM. How much RAM is in the Raspberries? Yeah, 2, 4, maybe 8 GB. Okay, but let's just say 4 because that's what's in the ones I've got. Okay, uh, how many bits does it take to encode 4 GB worth of locations? It takes 32 bits to do. The max that you can do with 32 bits is 4 GB. Okay, and the reason is what's 2 to the 32? It's like 4 something billion, right? Well, there's 4 GB. Okay, so this was sort of a problem in the 2000s because sort of the later into the 2000s, because computers back then, like let's say you'd get 2 GB, and then there were some that were starting to come with 4 GB of memory. Well, what happens if you build a computer that's got 8 GB of memory, but you only are using 32 bits to encode the locations of memory? How much of that memory can you actually use? Only 32, or sorry, 4 GB worth. Okay, and the scheme for how many bits you're using for the memory locations depends on 2 things. It depends on your processor's architecture and the operating system that you then run on it. Okay, so the Raspberry Pi, what's the architecture? It is a 64-bit processor, which means how big are the memory addresses that it deals with? 64 bits, which means it can address 2 to the 64 bytes mailboxes, which is an astronomically huge number. We'll never run out of that. Okay. Okay. So these pointers are 64-bit integers. They're just mailbox numbers, okay? And because they're 64-bit, that's why I used the %LX there. L because it's a long integer, 64 bits. Okay, and then why did I put the X there as opposed to an I? I could have put LI there instead of LX. The reason that I did so is because I wanted this information to be displayed in hexadecimal rather than as a decimal number. Okay, that's just the way I wanted it to display. Okay, so is that okay? All right, so let's run this and see what it tells us. Oops, don't need to go there. I need to go down here. Okay, so what do we get there? The string is located at 7FE0C769D8. Okay, whatever, right? That looks like it's effectively a random number, and in some sense it kind of is. And it may actually be different if I rerun the program, right? So it's not necessarily always exactly the same. The 7F part at the beginning is, you can somewhat reliably count on that, but not necessarily. Okay, so what this means is that the first letter, the H, is in that memory location, okay? And where is the E? Okay, so we've got blah, 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 A8. Where's the letter E? Huh? It's going to be in blah, 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 okay, it'll be a 9. The last digit will be a 9. You guys don't seem convinced. Yeah, the E of hello. Okay, so if the H is at memory address blah, 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 D8, that's the H's location. Where's the next letter? D9, and then what's after D9? DA, hexadecimal. Okay, whip crack. Okay, so now how do I know that? How do I know that 1 byte down is going to be the next letter? Well, yes. I mean, wouldn't it make sense for the string to be in order, right? That'd be kind of silly if it was just like the H is over here and the E's way the hell over there, right? Like that's stupid. Okay, but how do I know that it's exactly 1 byte to the next letter? Well, how are characters encoded? In bytes. In ASCII, 1 byte per character. Yes? Okay, now let's contrast that with my array. Okay, I made it out of integers, correct? All right, so let me make the exact same construction here. Oops. So let me do this exact same thing, but instead of the string, I'm going to do it for the array. And what did I call the array? My array. Okay, so, all right, so there we go. All right, so my array is also in memory someplace, and its starting location is, say, B00. Okay, great. And then the string is located starting at B18. Okay, fine. Now you might ask, why is it that the string is a higher number and the other one's a lower number? Well, who did I define first? I defined the array, not the string. Okay, it's just I'm printing them in the opposite order. So okay, whatever. So if the digit 3, okay, that number is located at starting at B00, actually, which memory addresses have the number 3 as an integer? Okay, so how are integers stored? Well, I've mentioned it before, but how many bits are needed to encode an integer? 32 bits, okay, on this modern architecture. Okay, what about if it was a long integer? How many bits would it be? 64, okay. So because I use data type int, not long int, my integers here take 32 bits each to encode. How many bytes is that? 4 bytes, right? Because it's 8 bits to a byte. Okay, so every number that's in my array takes 4 bytes to encode, whereas every letter of my string only took 1 byte to encode. Okay, so like you not only need to worry about where the thing starts, but also how many bytes do you need to go down until you get to the next object in your array? Well, it depends on what data type you built your arrays out of. If they're integers, it's 32 bits over to the next dude. If it's strings, it's only 8 bits over to the next dude. If it's double precision floating point, then it's 64 bits over to the next dude, the next entry in the array or the list. Okay, does that kind of make sense? Okay, so these pointers are things we're going to really, really, really have to care about. Okay, and while we're on the subject, then let's kind of look at how this stuff is encoded in memory. Okay, and actually look, sort of peek at memory in a sense. Okay, so I'm going to do one thing different. And instead of executing the program as is, so I'm going to remove this and I'm going to add an extra flag -G. Okay, so I'm still going to compile it, but I'm going to compile it with this extra flag, the G flag. G stands for debugging. Okay, so I'm going to run that. And then I'm going to use a program, a debugging program, to watch this program executing line by line. And that program is called GDB, for GNU Debugger. And I'm going to run it by GDB and then // in the name of my executable. Okay, so I'm going to put a breakpoint in, and now I'm going to start stepping through. Oops, sorry, I've got to hit run first. Okay, so it just hit the very first line of my program that is actually doing something. Okay, it has not actually executed this yet, but it's about to. Okay, and then if I hit step, it will go on to the next line. Okay, and let me keep going. Oh, okay. Actually, hang on one second. I need to add another flag here. Okay, don't worry about what I just did. I'll explain that later. Okay, so I'm going to step through and, okay, so you notice it just printed the 3 there, okay, and the 13 and the 14 it's printing, those are the line numbers that went with the code, okay, and I'm going to keep going to this one here where it gives me the location of my string, okay, and then what I'm going to do, okay, is I'm going to basically have it show me what is in memory starting at that location. Okay, so I'm looking here at a section of the memory, okay, and what we want to do is sort of look at, okay, this, we should see hello here. Do you see hello there? I do. 48, that's ASCII for capital H. 65, ASCII for capital or for lowercase e. 6C and 6C, those are the two L's. And O, lowercase o is 6F. The exclamation mark is 21. And then there's 00, which tells me that I've hit the end of the string. Okay. So it's there. You just have to be able to read ASCII and hexadecimal, which is why you guys hope that one of the nerdy astronauts brought his ASCII table with him. Okay, or you look it up online, which is what we do, right? Okay, so there it is in memory. Okay, and if we went up a little bit, okay, so I'm not sure exactly how far to go up. So let me just do, this is probably too far. Nah, that'll work. Okay. So do I still see my string? You see it? Okay. Down there at the bottom right. Okay. What about the array? What was the array? 3, 1, 4, 1, 5, and so on. Do I see that anywhere here? Oh, looky there. All right. Why are there all those zeros? Nope. Because it's not a string, it's an array. Right? So the number 3, how is that encoded? How many bits did it take to encode that? It's an integer, so 32 bits. And each one of those little chunks is a 32-bit chunk of data. Okay? And there's the 3, and then the next chunk is the 1, and then a 4, and then a 1, and then finally the 5, which is on the next row, and the 9. Okay? Is there anything here that tells me that I've actually hit the end of my array? Because what's immediately after the array? The string. Okay? So I would have to know or somehow store the fact that my array has 6 things in it and not try. So, like, let's say that I tried to access. So if the 3 is my array bracket 0, what's the 9? Where is he? Yeah, my array bracket 5. Okay. What would happen if I tried to access my array bracket 6? Now, the compiler won't let me do that, fortunately, right? Because it's going to say, wait a minute, bro, you can't access the 6th thing in a list that's only got 5 things, it goes up to 5, right? Okay, but if I sort of overrode that, and if you do this in assembly, you can, I would go, where is the 6th, or sorry, where would my array of 6 be if it existed? It'd be right here. And I'd pull in string data as if it were an integer, which is gobbledygook. Okay. And if I started processing with that data, I might get complete erroneous computations and my program might crash and the world is going to explode. And right, like that's a bad thing. Okay. So you have to be careful about what memory you access. Yeah. Okay. So we'll talk way more about pointers and stuff and memory later. Okay. And in particular, we also will need to at some point talk about how floating point numbers are encoded because that is a whole, it's not, well, okay, it's both hard and very easy. It's essentially scientific notation. Okay. But we'll talk about that. Um, Okay, so I think that's pretty good for today. I'll post some new stuff for you guys to work on. Yay! All right. See you guys later.